We've done now area between a curve and the x-axis, which was just the integral. We've done area between two curves, so you have to subtract the curves and integrate. And our final piece is talking about volumes. I'm going to go ahead and apologize up front because I am not an artist, so I struggle trying to draw the pictures on these. You guys just have to use your imaginations, okay? I'll do my best, but my best is not very good on these. Just gonna throw that out there. Okay, so we have some volumes. We've done lots of volume stuff, and we have all these formulas. Every time you had to calculate the volume of something, you looked at the formula in your book, right? Remember talking about volumes of a cube or a sphere or a pyramid, those kinds of things. So let's talk about this first one. If I have a cylinder, okay, this is not your normal completely circular. This one has a flat side. But if I were to calculate the volume, what I have to do is take the area of the base times the height of it. And that's how all of these volumes that we've done have been calculated. When we talked about a cube, length times width times height. Well, the area of the base was the length times width times the height of it. When we talk about a circular cylinder, then area of a base, well, the base is a circle. Area of a circle is pi r squared. And so this one becomes, the volume is the pi r squared, the area of the base, times the height. Now the rectangular cube, area of the base is your length times width times the height. So that's where these formulas come from. Now the problem is not everything is something where the base never changes. You know, if you're talking about a pyramid, as you go up, that base gets smaller, right? If we took this kind of object, okay, there is no one formula for area of the base because anywhere I look along that, the base is a different size. So we start talking about cross sections here. A cross section is like a slice. If I cut this thing right here and then looked at that figure, what would it look like? Okay. When we do that, we have to, if I wanted to calculate the volume of this, I would have to come up with a formula for the area of that cross section. A formula because it's not the same every time. You know, as I'm moving along this shape, that cross section gets bigger or smaller depending on where you're at. But if we can get a formula for that and then take it times the length of the whole thing, we can still get our volume. So if we're trying to figure out how to do that, you know, if we go back to our very basics, we could do it like the very first time we did areas under curves. We did those Riemann sums. Remember those? So we would have this, we would break it into 5 rectangles and then 10 rectangles and add up all those areas. So we could do the volumes of all these little cross sections. I could take my blob and divide it into 5 pieces and add all those little volumes together. Or 10 pieces. And we know that if I want it to be more accurate, what do we have to do? More and more pieces. And so we were eventually doing the limit as the number of those pieces went to infinity to get the most accurate answer. So the volumes would be the sum from one to n of the areas of your cross section times the width of your cross section. But if we do the limit as that goes to infinity, that is really the definition of the integral. So our actual volume will be the integral from your starting to your stopping of the area meaning the area of a cross section, times your dx. Okay, so when you found areas under a curve, you integrated the height of that curve. If I want the volume, we are going to integrate the area. Okay. So let's take something that we know the formula for, volume of a sphere, 4/3 pi r cubed. I've given you guys that on tests. You had to find volumes of things, and I would tell you this formula. So how about we actually get the formula ourselves and see where it comes from? Because you guys don't trust me when I tell you things. You need me to prove it to you. I'm sure you've always wondered if that formula was really accurate or not. So we have a sphere, and this is where my apologies for my drawing come into play, because I'm just going to draw a circle, but it's a sphere. Okay, so we're talking about like a basketball, not just a flat circle. All right, if I'm going to put like an XY axis, so my X and Y axis would be like going through this center of my basketball. If I were to take a basketball and put a pole through the middle, the origin is at the very center of that basketball. Does that kind of make sense? So when I go to integrate this, we need to go from left to right. Okay, if this is the center, what would be the distance from my center out to the edge? That's your radius, right? So if you go in the negative direction, this point would be negative r, and if you go in this direction, that would be positive r. So we will integrate from negative r to positive r. And what we need is the area of the cross section times our dr. Okay, so now we need to figure out what the area would look like. If I take my basketball and I slice off the top and then just look down, what shape am I looking at? A circle. Can we agree with that? So the cross section is a circle. How do we find area of a circle? Pi r squared. So we have pi. Now, I have to be careful. I can't just put an r in right now, because r here represents the radius of the total thing. If I slice off just the very tip, is that the same radius as if I slice it a little bit further down? No, that radius is changing. So I need an equation for what that radius will look like. Okay. So how am I going to figure that out? Let's use triangle here. So this distance would be my horizontal, that could just be my x. My vertical distance would be my y. And this is my r, right? The radius is the same. So wherever I'm at on this circle, the distance from the center out is your radius. Okay, so if I am trying to get the radius at any given point, that length of the red line, that is going to be given by what? Which variable? We could measure that in terms of y to find the height of my circle. So let's talk about that. We have a right triangle, so we could say x squared plus y squared equals r squared. So if I'm trying to find my y, then your y could be positive or negative. We are going to keep things simple for now. Let's just deal with the positive. So y is the square root of r squared minus x squared. Okay, that would give me this point on my circle, no matter where I'm at. So when we find the area of a circle, we have pi r squared. So my radius that I'm going to be using is r squared minus x squared. guess technically the way I have this set up, we could have done it either way in terms of X or Y. It might make more sense if I draw my red lines like this. If I got rid of my Y. Because we could cut off either the top or the side of the basketball, right? Since we are integrating from left to right, I really want to cut off a side. So that's why my radius is just my height. Is that a little more clear if I draw it like that? Okay. Let's integrate this thing. That should be a dx, not a dr. X is my variable that's changing. Because the radius of the entire sphere doesn't change, right? Just where you're at on that point. If you square a square root, what happens? Cancels. Okay, pi is just a coefficient, so it can stay. X is my variable here. That means r is just another number. So what would be the antiderivative of r squared? R squared x. Minus, what's the antiderivative of x squared? 1/3 x cubed. Okay. So if I plug in r, I get r squared times r, so r cubed minus r cubed over 3. Minus, if you plug in a negative r squared times negative r is negative r cubed. Minus negative r cubed would be a positive. So if you add your coefficients, 1 plus 1 would be 2, minus 2/3. So 2 is like 6 over 3, minus 2 over 3 is 4 over 3. And isn't that what we said it was? 4/3 pi r cubed. So that is the formula for volume of a sphere. Let's calculate some with fewer variables and more numbers. I think it makes a little more sense when we do that. Are there any questions on this example? So find the volume V of the solid, I call this D, whose cross section at x is a semicircular with a radius of x squared for x between 0 and 1. So this is what my picture looks like here. Okay, I gave you some information about it, which is how I drew my picture. My radius was x squared, so this is y equals x squared, so it's part of a parabola just between 0 and 1. And so if you start off if I took a parabola, if I just took the chunk between 0 and 1, that's where that little curve came from. Okay, and I created a solid around by that, which we'll talk more about later, but here's this picture. Okay, I'm just asking you to find the volume of this picture. So when we find the volume, we have to integrate the area of the cross section. X is going to be my variable. Where does my x start and stop? Starts at 0, stops at 1. I gave you that. we're integrating them in terms of x, so that's a dx. I need the area of the cross section. So the cross section here, no matter where I slice this, if I just took a vertical slice, we are looking at a semicircle, which is half of a circle. How do you find the area of a circle? Pi r squared. So if I only have half of a circle, it would be 1/2 of that. Okay, my radius. If the radius goes, as you move along this, the radius is going to be measured by this curve. But depending on where you're at on the curve, you have a different sized radius, correct? So, what's the equation for my radius? I told you the radius was x squared, so if you plug that in for your r, we get 1/2 pi x squared squared is x to the 4th. Or here, for the sake of your notes, I'm going to write it like this for a second so you can see exactly where that came from. So my radius was x squared, so I plugged that in for my r. That's the hard part, is setting these things up is what's tricky. After that, this is a basic integral. 1/2 pi, that's pi over 2, that's just coefficient. You can pull that out if you want. So the antiderivative of x to the 4th would be 1/5 x to the 5th. 1 to the 5th is 1, minus 0 to the 5th is 0. So we get pi over 10. So the volume of that figure is pi over 10. Questions? Let's look at some more. So I want the volume of the solid, so this time I'm making you draw your own picture, obtained by rotating y equals 1 minus x squared, bounded by y equals 0 around the x-axis. So here's where you get to be very critical of my artistic abilities, and I hope your pictures are better than mine. So, let's start by graphing this. Y equals 1 minus x squared. Okay, if I were to start graphing that, if I plugged in some points, like if x is 0, y is 1. If x equals 1, you get 1 minus 1, which is 0. If I plug in a 2 for my x, what kind of y do we get? A negative. But I told you it was bounded by y equals 0. So that means we're only graphing the part above the x-axis. If I plug in a negative 1 for my x, 1 minus negative 1 squared is 0. Okay, this thing is an upside down parabola, but I only need that part of it because I said it was bounded by y equals 0, so we weren't looking at the negatives. Alright. Now I'm going to take this. So I have this little semicircle, and I spin it around the x-axis. So if you take that little U and start spinning it around the x-axis, what do you form? A sphere, right? A ball. All right. I cannot draw a three-dimensional ball, so you get a circle with me. I'm sorry. It's the best I can do. But we know this is 3D because I didn't just reflect it over the axis. I spun this thing around. So it is three-dimensional. We have a ball. So, my volume. Okay, we can integrate these things with respect to x, with respect to y. Based on this equation, since it's y equals, I think I want to keep things in terms of x's. So if you are integrating with respect to x, your limits have to be x values. So where does this thing start and stop if I'm looking at my x's? -1 to +1. Okay, so I'm integrating with respect to x. When I talk about a cross section, so if I make a slice, if I slice this thing right here, we would be looking at what kind of shape for the cross section? A circle. If you take your tennis ball and you cut off the sides, you're looking at a circle for the cross section. So area of a circle is pi r squared. So we need a formula for the radius. Now wherever I'm at, if I'm right here, the radius is the distance from the axis up to the curve. If I'm here, distance from the axis to the curve. So the radius is just the height of that curve, which is 1 minus x squared. That's the equation of that curve. Okay. Questions on how we set that up? So that's the hard part. Now we just start working through this. So I could pull out my pi. I'm going to FOIL this because I can't do a substitution. I don't have an x on the outside, so we need to just go ahead and square it. So that would give me a 1 minus a 2x squared plus an x to the 4th. So antiderivative of 1 would be an x. Antiderivative of 2x squared would be 2/3 x cubed. Antiderivative of x to the 4th would be a 1/5 x to the 5th. So if we plug in a 1, get 1 minus 2/3 plus 1/5 minus, if you put in a -1, okay, so if I distribute, I get 2 minus 4/3 plus 2/5. Let's practice doing this without a calculator. What would my common denominator be? 15. So this is like a 2/1. So if you multiply by 15 on top and bottom, you get 30/15. Multiply this one by 5 minus 20/15. Multiply that one by 3. So plus 3/15. So we get
plus 6/15.
Yes, thank you. So 36 minus 20, so we get 16 pi over 15. And that is our final volume. Questions on that one? do one or two more. We'll see how much time we have after this. Okay, find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals the square root of x from 0 to 1. So we need to start with a picture. Okay, my curve is y equals the square root of x, which hopefully you know what that looks like. If not, you could plot some actual points. And I am going to rotate that about the x-axis. So I'm going to take this and start spinning it around the x-axis. So it looks like this. We are going from 0 to 1. So we should get this little curved cup looking thing. Okay. From here, set up our integral. Where does it start and stop? Okay. We have to set up, it's the area of a cross section. So a cross section, if I took a knife and sliced it back here, what shape are you looking at? A circle. So area of a circle is just pi r squared. The radius is just from the axis up to the curve, so it's just the equation of that curve, which is the square root of x. Does everybody see where I'm getting that? So now we can integrate. The square root of x squared is just an x. So if you want, you can plot pi, antiderivative of x would be 1/2 x squared. One squared is 1, 0 squared is 0, times pi over 2 is pi over 2. Let's stop there for today. You guys are ready to try a couple.